and the project that the FreeBSD Foundation sponsored in 2009. And we'll start with what are the advantages of wireless mesh networks, and then I'll move on to explain the specification of the wireless mesh networks we used, and then I'll move on to some implementation details. So this is the most common wireless network setup, and it's actually the one used in this building. There are a couple of access points connected to a network wired, and then there are probably some routers in between. And this might not work for you if you are in an area where there are no wired networks, or you can add one, or because it's just too pricey. Sometimes the wired network must be in fiber optics, and that's even worse. So then you also have the problem that the bandwidth is shared by all the same stations. Well, the good thing about this is that it's very easy to set up. It's not that the mesh networks aren't that easy, but this is a little bit easier. So, what exactly is a wireless mesh network? So, this is not a new topic, and it's been around for some decades, I think. And the idea is that we can use the wireless medium to join our previous setup. And instead of using cables, we'll be using wireless too. So the problem becomes, how can we route the packets, and how can we best achieve how can we calculate the best path, and along other metrics that we need to figure out. So the other thing is that there's no central access point, there's no node that could fail, and there's actually dozens of technologies that have wireless mesh network functionalities. The one that we use, and I'll talk about today, is 802.11s. The advantages of the mesh networks are quite straightforward. If you have already a wireless network, you can expand it by just buying another access point or buying another embedded system, and there's no need to run wires, and it will just find the other node, they'll internet connect, and then you can move forward. Because of the no wires thing and the added maintenance of it, it can be much lower in cost than the solution that's in this building, for instance. So the other advantages is that you can build a wide network with wireless mesh. And for instance, we could build a wireless mesh network all in this building and across all the floors, and we didn't we wouldn't need any kind of wires or anything complex. We just needed to plug in, you'll find each other, and the route packets between each other. And that's possibly the main advantage. So I showed the picture of a wireless mesh network on the presentation slide, and there's new names for it, like anything else. You need new names. So on that mesh network, there are 9 mesh stations, and 3 of them interconnect, and they are called mesh portals, which is just a fancy name for a bridge. The whole group is called Mesh Basic Service Set, MBSS. This means that we can connect by using bridges to other 802.x networks and eventually to the internet. And the whole thing is called Extended Service Set. So as I said, there are plenty of technologies that are in use, and 802.11s is used a lot on the OLPC XL1 children's laptop. It's, as you probably heard, it's a laptop for children in developing countries, and previously they used a Broadcom protocol, and this protocol is exactly the same as the 802.11s, but now they moved to 802.11s, I believe. The other mesh networks are using the routing protocols in above layers. So one thing special about 802.11s is that it works on layer 2, while other products usually work on layer 3. It's not always the case, but it's very common for a wireless mesh network to work on layer 3 and using the radios in ad hoc mode. So Meraki has a special mesh product that's mainly for long-range applications, and Mesh Dynamics' main client, I think, is the USA government, and they have they built actually a mesh network to be used by soldiers and tanks, and the soldier goes away from the tank, the mesh network detects this and tries to find another route to the soldier, and then some tanks move together and they'll build a new one. It's a special thing, and it has 3 radios. Each soldier and each tank has 3 radios with a special configuration. 2 of them are for transmitting. It's if you Google Mesh Dynamics, you'll find with some very cool images. SMesh is a company that does mesh networkings with fast roaming. This is useful for voice over IP applications, and that's what their main application is, voice over IP, where you have a cell phone inside a mesh network and you're traveling, and fast roaming happens very fast, hence fast roaming. Anyway, Solar Mesh is a mesh application where they have solar panels The Sonos multi-room music system is consumer product, and they use a mesh network in the following way. You can have in your house 3-4 stereos, and each of the stereo has a Sonos appliance, and this Sonos appliance builds a wireless mesh network inside your house, and whenever you want to use the stereo on another room, you can do it because they're all interconnected, and this happens without the user ever thinking or getting an idea of what's going on. So in the paper I also wrote that there are so many mesh networks that it's probably that we have used the mesh network without even knowing about it. There are some more examples in the paper. So I'm going to talk about 802.11s, and it's the IEEE answer to wireless mesh networks. So I guess I figured that this was so popular among wireless companies that it was time to build their own standard. And as I said, this works on layer 2, and it basically keeps the MAC header unchanged, which means that it keeps backward compatibility, or actually it doesn't interfere with the wireless networks that we're using right now. And it's based on top of 802.11 and 2007. It's under draft. I'm not sure when it's gonna be final, but maybe in 2011, maybe, I don't know. It's hard to predict. And one of the main goals in 802.11s is that you can use your own routing protocol and your own link metric and your own encryption protocol and your own authentication protocol. So FreeBSD actually has support for this, and you can even I haven't done it yet, but we could build a kernel module that interfaces with the user LAN to implement a routing protocol for the mesh. But right now all I have implemented is a model of a framework where you can program your routing protocol and then load it in the kernel, register it with the networking stack, and then use ifconfig to select it. But I'll show that later. So each mesh station is actively looking for other mesh stations every time, and this happens by each mesh station broadcasts a beacon, like an access point, and if each of these stations are broadcasting beacons, then mesh station 1 will get beacon from station 2, station 2 will get a beacon from station 1, and station 3 from station 2, station 2 from station 3, and they'll peer with each other. And this is the first step in creating a mesh network. Then with routing algorithm, the mesh station 1 can talk to mesh station 3, and so on. If we have another one, you'll be able to talk to each other by using the middle nodes. So if you want to build a specific specific network topology, you can use access control lists from our stack, and they'll stop from talking to each other and trying to peer. So this is the new mesh header and the place where it's placed. On the first figure, we have the usual MAC header of 802.11, and the mesh control is what I call the mesh header. This is just for data packets, and there are some flags but it's nothing special. There's time to leave a sequence number, and the address extension is to make the header a bit larger so we can store more addresses. And this is needed for bridging, because whenever a packet comes from a bridge inside a mesh, the packet will have the source from outside the bridge, the next station for inside the mesh, and the destination station if the destination is outside the bridge. So we need about 3 addresses inside the mesh and 2 addresses outside. So it will be like 18 bytes. So the algorithms that 802.11s implements, as I said, for routing and the airtime metric are first for routing is HWMP. I will explain HWMP in a short. Ready to go aware OLSR is another routing algorithm that you can use. This is the one that's not yet implemented on FreeBSD, but it could. It's not hard to do it. The link, there's this link metric algorithm is used are used for measuring the link between 2 mesh stations, and we base this information from the transmit rate and the error rate. This is needed to assure us that we're getting the best link inside the mesh. So there could be many ways for a packet to reach the final destination, but with airtime we are trying to pick the best one. So PSI is something that I haven't done yet. It's authentication and the simultaneous authentication of equals, being the mesh stations. It's used when there's a pre-shared secret. But I hope to actually implement authentication and encryption sometime in the near future. Well, HWMP is a routing protocol created exactly for 802.11s, and they based it on AODV, and it's very based on AODV. It actually has the packet formats are very, very similar. The packet format names are also very similar, and this is an on-demand protocol. This means that whenever you want to find a station, you broadcast a packet with a path request. This path says that, hey, I need the path to this station, I'm over here, so everyone will broadcast the path request. I'll show you an animation for it in a second. So then 802.11s actually IEEE extended HWMP to enable proactive routing, and proactive routing is just a simple name for when we could pick one mesh station to be a root mesh station, and this root mesh station is broadcasting path requests by every second and saying, hey, I'm here, if you're new and I don't have a path for you, please make a path. And this is actually useful because if a node joins on a very crowded mesh network, if there's a new node, this node will have a routing table that's empty. So if this node is nearby a root mesh station, the root mesh station has a big routing table and can tell the new node very fast that the destination, which destinations do the new node want. For instance, if there are many hops, the on-demand routing requires a couple of seconds, but if the new node is nearby a root mesh station, it will just take half a second. And this microphone doesn't like me. So the name hybrid comes from being on-demand plus proactive. So common scenarios on HWMP. For instance, on this mesh network, let's say that station 1 wants to find a path to station 8. Station 8 is some hops away, and station 1 broadcasts a packet saying, I want to build a path to station 8. Then station 5 and 3 will get this packet, and since they're not station 8, they will broadcast it again to the nearby stations. And you notice that station 3 will broadcast again to station 5. But station 5 already had this broadcast, so we could be having a loop to infinity situation here, but that won't happen because the HWMP management frames have sequence numbers and also time to leave field. So station 5 will discard this packet, but will send to station 7, and station 3 will send to station 4. So this will happen again, and eventually station 8 gets a path request message from station 1. So now station 8 has to reply to this packet, and the animation doesn't show it, but now the packets are in unicast mode, not broadcast. But since station 8 got 2 packets from station 6 and station 9, the station will send a packet to each of these stations. So it will travel back again, and it eventually reach station 1. Let's say that this is probably the best path to station 8. Now, when the path request and the path reply happens, the intermediate stations will also build a path to every node in between. If this was not the case, we could have station 1 will know the path to station 8, and then we'll try to send it back to station 3, but then station 3 will drop it because it doesn't have a path. So to speed up things a little, when there's a path request and a path reply message, the intermediate nodes will also build a path. So another thing that might happen is when a node goes away. So let's say that node 9 goes away. Because of the fact that node 9 will stop broadcasting beacons, all of the stations who were peer to station 9 will figure this out, and they'll say, hey, station 9 went away. So what should we do about it? They're going to broadcast a packet saying that station 9 is away, so we can't talk to it any longer. This packet is a path error packet, that management frame actually. So everyone, in the mesh network will delete the path to station 9 from the routing table. So as I said, HWMP uses sequence numbers, and we're constantly tracking the last sequence number seen, and we also implemented a queuing mechanism on the wireless stack to hold buffs while the packet, the path is being set up. So on our wireless stack is called Net 802.11, as you may have heard, and we were the second implementation of 802.11s, and we released FreeBSD 8 with 802.11s support. FreeBSD Foundation sponsored it in late July 2009. We had working implementation. In July, we couldn't speak to Linux machines because Linux was actually following an older draft specification, so the packets formats were a little different. But in October 2009, the Linux code changed to reflect the latest standard, and so after that we could build mesh networks with FreeBSD and Linux. So we actually changed 3 drivers, but many more can be changed, especially the USB ones, because I haven't touched them yet. As a general rule, if your driver can do host AP mode, it can most likely do mesh too. The thing is that the host AP mode works very similar to the mesh node, and in Utero's hall we actually map the mesh mode to host AP mode, so there's no much difference. So there are some new modes, new commands to ifconfig, and we see that, let's see if this works. Okay, so there's the new wireless LAN mode called mesh. You actually have to specify a channel because every mesh network needs to be on the same channel. And there's a mesh ID which is very similar to the SSID you probably know. And it's the same here. New things are the time to live of the data packets. If we allow peering to happen, if we forward packets, the name of the link metric algorithm, the name of the routing algorithm, the mode for the root mode for HWMP, the number of hops we allow on HWMP packets. These are the packets for setting path reply. So if we want to build a mesh node and limiting the number of hops each node should be able to talk to, we can change this parameter here. So this is the same list station but with a modified output. These numbers are peering instances numbers, so we paired with this node and our peer ID is this one, the remote peer ID is this one. So the most important thing here is the state column. If this isn't in established mode, you won't be able to talk to this node. But the thing is, I'm showing just a mesh network with 4 nodes, and this is not related to the next one. So let's say this network is able to connect to each other without no intermediate nodes. So the next is transmit sequence to receive sequence, and this new command was added to list the mesh routing table, and we see here that we have the mesh network and 2 nodes go through this one here and this one here goes through. So in fact the node where we issued this command only has 1 peer, and since this peer here is connected, we are connected directly to it, there are no hops, but the other destinations all go through this one. So it's like this one is in the middle and the others are far away. Let's see, this is the root mode setup. So this is not very important. Now there are 3 root modes in the spec, and each one has a way of trying to find other nodes, and this one actually uses a different management frame, and this one's use the regular path request frames. So regarding to performance, for 0 hops we have the same performance as analog mode, and as a general rule the performance drops about 50% with the number of hops. This is an example. You could get an H211 and card, which will make things faster, or we could implement MCCA, which is a time division thing, and hopefully the penalty for each hop won't be as high as 50%. And this works like each mesh view will set up a time slot to send packets. So if they are all synchronized, each of them will send packets on a very short time, and there will be no collisions, and hopefully that will be a lot better in terms of performance. So, as I've been saying, the FreeBSD Foundation sponsored this project. Sun Life helped a lot. The GateWorks Corporation sent me one ARM board. Cosebit is a company that did the Linux implementation of 802.11s. They also have Wireshark patches. We actually work with them to make them better. And I'd like to say that it's very important that you keep sending money into the FreeBSD Foundation. There's more information, especially regarding to how we can build a routing protocol without touching the stack by using the framework that I built on the paper. There's also this wiki page which hopefully has a lot of information that you might need. This is the website for 802.11s, and there are some more ideas here, actually. Some more things that I might have missed on Wikipedia, and this is the website for the Linux implementation. So if you have any questions, I can answer them now.
So you mentioned FreeBSD and Linux. Is there implementation in any other operating systems?
Well, Dragonfly BSD is syncing the wireless network stack with us. So they'll have wireless mesh network support in the very near future. If NetBSD syncs the code with us, they'll have mesh support. This is basically, if you sync with FreeBSD, you have mesh support. OpenSolaris also has a FreeBSD mesh wireless stack, so if they do it, if they sync again, they'll have wireless mesh network.
Okay, but nothing for macOS or Windows, right?
Well, macOS is actually using the FreeBSD stack,
right,
but in very novel ways. So it's a possibility that Apple might use this one in one of their products because they actually have wireless distribution system. WLVS support. So this is like the next step for them. More questions? Well then, thank you for listening.